Hello again and welcome back to functional programming course. Now let's talk about lazy computations in F sharp. So F sharp, as you know, is the applicative programming language. So it's eager. It computes all arguments of a function before calling it. But there are some cases when we need to have lazy evaluation. And one of the examples we have seen already during the tree traversal. When we want explicitly to delay function execution, we can use this fun construct to create a function which will be executed later on. But there are also other ways to enforce laziness in F sharp, and especially constructions called lazy and force. And let's see how they work in an example. First of all, let me define the functional f of x, which would explicitly return value x, but we will also print something like creating x and return x. So if we compute f of 1 plus f of 2, that would result in calling the function f 2 times and the result 3. So it will print creating 1, creating 2, and then give us 3. So what we can do here, we can say let x equals f of 1 plus f of 2. Let's see how that works. If we execute this, f of 1 and f of 2 is executed immediately because x is not a function, right? And we can delay this by saying something like this. This will not call the function f, and the execution would be delayed. But x would not be a value, it would be a function. There is another way to enforce laziness here, is to use the lazy construction. Lazy is a keyword here in the programming language, which encapsulates the expression into the special type called lazy of int in this case. So you see what happens here is when I define x to be lazy of this expression, it does not evaluate the expression. It encompasses this expression and packs it and makes it a part of this type lazy of int. And you see that x, when I call x, it tells me value is not created, because when I try to access x, it does not evaluate an expression. Only when I try to access x.value, actually functions are executed and I get the result 3. And x.value has the type int. After that, if I call x, you see it prints lazy of int equals to 3. So once x is computed, all other calls to x value, they return this value without actually re-evaluating it. And this is something called memoization, because we remember the value computed for this lazy expression. So the way it works, again, lazy of expr returns something of type lazy of a, and then there is also a special thing called force. In addition to calling dot value, you can also use force to force the computation of the lazy expression. So force expects the expression of type lazy of t and returns the value of t. How can we see that in action? So suppose we want to define the lazy definition of factorial. So in this case, what we can do, we can say lazy factorial. For 1, it will return lazy of 1. For n, it will return lazy of n times lazy.force, lazy factorial of n minus 1. And we can also take the advantage of the fact that lazy is the keyword, so we can provide it with larger expression. So we can say that lazy factorial is lazy of, and then we would do the matching operator. So we will say match n with, for 1 return 1, for n return n times lazy factorial n minus 1. Then we need to say dot force to convert it into integer value. And here we return 1, but because it is an argument of a lazy expression, it will be converted to lazy of 1. So this lazy factorial, it gives us back the lazy of int result. But there is not actually much use in defining lazy factorial, probably, but there are cases when laziness comes very useful. Another interesting example is lazy lists. The way sequences are implemented in F sharp is somehow not really functional, because I have already explained that sequences rely on generators. Generators are essentially functions which return the new value each time. So sequences are somehow, they rely on this functionality. In other functional programming languages, and especially in the lazy functional programming languages like Haskell, normal lists, they are lazy, inherently lazy by design, because all constructors are lazy. And we can emulate this functionality in F# by using explicit laziness. So here I will call this lazy list a stream. Maybe not a very good name, because we have talked about streams just before, but this is the different kind of stream. I will call it stream just to distinguish it from sequence. So here we can say the normal list, it consists of the cells constructed using cons constructor, which takes a and a list. But here each cell would be not of type a times a list, but the type of a lazy cell. So here we would say that the stream would be the lazy value of a cell, and the cell would be either nil or cons of a and a stream. So what it means is that each cell would be kind of encompassed by the lazy expression. So for example, if I want to define the list 1 to 3, I would say it's lazy of cons of 1, of lazy of cons of 2, of lazy of nil. What's the reason of that? The reason for that is some values inside the list might not be evaluated. They might be evaluated only when needed. And we can operate on those lazy sequences. For example, this is lazy concatenation, and lazy concatenation would need to unpack the first list, and it will need to go through the first list and say, okay, if it's nil, then we return the second stream. If it's cons of x and y, we return the lazy constructor of x and concatenation of y and t. So the way this lazy concatenation works is that we need to unlazify, kind of. We need to go through the first list as a normal concatenation, as a normal append, but the second list stays intact, which means that concatenation cannot be applied to infinite lists, and that sounds quite logical, because we need to add the second sequence to the end of the first one. It means that it should have some kind of an end. So while F# sequences is a .NET compliant way to implement sequences, this lazy and force lists is more purely functional way to deal with lists. And if you want to really get into how lazy lists work using those kind of lazy constructors, then it's best to have a look into Haskell programming language and how lists are implemented there. I have already mentioned the term memoization. We have seen that a lazy element can be lazy. It can sit there until it is evaluated, and then we remember the value for further use. And in all lazy programming languages, this is an important issue, because whenever we pass an expression, for example, to a function, and then it becomes split into several parts, we need to make sure that we evaluate this expression only once, in order not to create inefficiencies. However, memoization can be useful even in eager programming languages such as F#. So let's see one example when memoization becomes especially useful, and that is computing Fibonacci numbers. So suppose we have this traditional definition of Fibonacci, traditional non-effective recursive definition, which says that for any n which is more than 2, we call Fibonacci of n minus 1 plus Fibonacci n of n minus 2. Which means that for each call, we call Fibonacci function twice. Suppose we want to calculate Fibonacci of 5. It means we need to call Fibonacci of 4 and Fibonacci of 3. Fibonacci of 4 calls Fibonacci of 3 and Fibonacci of 2. Fibonacci of 3 calls Fibonacci of 2 and Fibonacci of 1. And then it continues in this manner. So you can see that we evaluate the same values, like here, Fibonacci of 3 many times. Fibonacci of 2 is evaluated many times, and also Fibonacci of 2 is evaluated here. This tree is binary, so it grows very fast. But most of the times we really evaluate the same values which we have already evaluated before. So to speed this up, we can say that we want to do memoization. We want to remember the results of a function for each argument value. And we can do that explicitly. For example, we can create a dictionary. This is .NET structure, .NET hash table, and we can use it in F#. We can also use F# map, but that would be a little bit more ugly to use. So we will use this dictionary. And then the Fibonacci function would look like this. We will check if we have the key in the dictionary. So if we have already memoized the result, then we just return the value. If not, we do the recurrent call. This is the recurrent call to Fibonacci. And then we add the result to the dictionary. And we return this result. So that sounds pretty obvious, like how to do that. And you can imagine that this would speed up the execution pretty significantly. Instead of having the binary tree, we would essentially, like if we have calculated already Fibonacci of 3, this whole second branch would be completely removed. So instead of a binary tree, we would essentially get the linear algorithm. However, writing this every time by hand is not the best idea. We know that in functional programming we can easily generalize the behavior and create functions which accept other functions. So let's call the generic memoization function, which we will call memoize. So memoize would return, we will expect a function from A to B and return the memoized version of this function. So and it will look exactly, well, not exactly, very similar to the Fibonacci example we've just seen. So it will create a dictionary. Then then it will return the function of n. If this n is inside the dictionary, then we return the value. Otherwise, we compute function f, add the result to the dictionary, and return res. Now, it's a little bit tricky to define the fast Fibonacci function, because if we just pass here our binary recursive version, it will not work, because it will only memoize the final result and not all the intermediate results. And that's why if we want really to memoize the Fibonacci, we need to define the function fibfast in this following way. We wrap everything with memoize function, and then inside this memoize function, we call this fibfast. We call already memoized version of the function and not the original. So this memoize, we cannot just pass any recursive function in and expect it to speed it up. Instead, in the definition of the recursive function, you need to do this trick. You need to wrap it by memoize and use calls to the memoized version of the function inside the loop. So to see how this speeds things up, this is the graph that I have just plotted trying to run all those functions. And you see that normal Fibonacci function, it significantly slows down after like values of 23, 24, and it goes exponentially up, while the memoized version of Fibonacci goes almost linearly close to 0, which is good, but we need to understand that we get this speed up at the expense of memory, because we remember all the intermediate values. On the other hand, because in this graph we only compute Fibonacci numbers up to 30, we don't use more than 30 units of integer memory to compute that. And this sounds like a really fair thing to do. So to summarize, we have seen that lazy computations can be implemented in the eager language, either by using just functions from unit to something, or we can use special constructions of the language lazy and force. We can also use lazy sequences, and memoization is a good technique that allows you to get some kind of compromise between memory and execution speed. And it can even do things like convert binary recursion, which is really computationally consuming, into linear algorithm. However, if you can do it just by improving the algorithm, of course it is much better. I'm not arguing that memoized version of Fibonacci is better than implementing Fibonacci using just one non-binary recursive function. Of course, it's better to think and implement something fast than to rely on memoization all the time.